Reservations in two-way slabs by means of yield lines. This video deals with case 11 to 15 of a part of a concrete floor where two adjacent sides are fixed and two other sides are simply supported. The dark green one is fixed or continuous, and the orange line is simply supported. This video will deal with case 12, which is a corner hole or corners reservation in the top left of the slab. And this reservation is following the yield line. Two-way slab means that B must be between A and 2A. Then we got the reservation B1, B2, and the reservation is following the yield line. So the top left corner means that D4 and D3 is 0. This is this point. The corner yield line means, of course, that D1 over D2 will be equal to S4 divided by S1. And only cutting one yield line means this goes up to here and not further. So it means that B1 would, of course, be smaller than B4. Now, these are the different types or the different elements of the reservation. You can see how it can grow and how it can move according to this yield line. Then we repeat the conditions, but then fill in the parameter S1 and S4. And so you will see that you have this condition is fixed. So the parameter that's left over is D1, and D1 must be between 0 and 0.634 times the smallest dimension of the slab. Let's look at the work done by the external forces. Then you will see that for the rectangular part of the slab, you got this distance, which is B minus S1 minus S3 times A, and the mean deflection is delta over 2. And then we go to the green elements, and the green elements are triangles. So we have A over A times A times S3, which is this, and A times S1, but we must subtract the reservation. We subtract that. So minus, and we have two triangles, B1 over D2 divided by 2, and the mean deflection is, of course, B1 over S4 divided by 3. And then the other side, it's this portion here. It's D1 times D2 divided over 2, and then the deflection is D2 over S1, 1/3 of it. Okay. Then we can fill in different parameters. The work done by the internal forces is we can calculate it by following the yield lines. We got here on top, which is B. This is axis of rotation, but that's the yield line of the negative bending moments. So you got B minus this portion here because it's cut. So it's B minus D2 divided by the angle of rotation, which is delta over S4. Then we got the same happens with this yield line projected on this axis of rotation, gives you also B minus D2 divided over S4. At the bottom, you got this yield line projected on this axis of rotation gives you B over S2. Then we got A over S3, and then again A over angle theta divided by S3. And what's left is this yield line projected on this axis of rotation, which gives you, of course, A minus D1, because the reservation is there, divided by delta over S1. We can fill in the parameters, and B must be equal to E, so we can have M then, and M is then equal to this expression. Let's give an example how to deal with this type of formula. Suppose we have a slab of 150 millimeters depth, 30 millimeters concrete cover, floor finish is 1 kilonewton per square meter, and the mobile load is 10 kilonewton per square meter. What is the needed reinforcement in this type of slab? In this case, 12 hole in it, reservation in it. First, we calculate the load in ULS, which is 1.35 current loads plus 1.5 mobile loads, gives you 21.4 kilonewton per square meter. We repeat the different parameters that we got in our example, and we can directly calculate from those three parameters the maximum bending moment. And the maximum bending moment is 15.4 kilonewton meter per meter. Then we transform that into reinforcement. The lever arm in X direction is 160 millimeters. In Y direction, 108. The mean lever arm is 112 millimeter. It means that the needed reinforcement is 1.1 times the maximum bending moment divided by 0.9 times 112 times the yield strength of the steel, which gives you 387 square millimeter per meter. This means 8 diameters, 8 will be okay, it's 402. Now let's go to a second example of an existing slab. It's 5 by 5 meters, fixed on two adjacent sides, simply supported on the other sides. The only thing we know is that the reinforcement top and bottom are equal, but we do not know the load where it was designed for, and the reinforcement that is put in. Now we ask ourselves, because they have to make a reservation in this lab, and we ask, is it possible to make a reservation of 2 by 1.15 meter in the corner there? Is it possible? So we calculate the maximum bending moment of the slab without the hole, without the reservation, but we don't know Q, so we divide M0 by Q, and we end up with a formula which has only geometric characteristics. We can calculate this, and we find 0.708 meters per meter. The maximum bending moment with the hole, from the formula of previous slides, we divide M by Q. We got this formula, and we have 0.789 meters per meter. This means that the bearing capacity is 90%. Or by making a hole like that in the corner, we lose 10% of the bearing capacity of this slab. Now, bearing capacity, we define it as 100 times the maximum bending moment without the hole divided by the maximum bending moment with the hole. Or you can put it like this. Then we know we are working in dimensionless variables. It means alpha 1 is B1 divided by A, and alpha is B over A. For the case 12 types of holes, then we know that alpha must be between 1 and 2 for two-way slabs, and alpha 1 must be between those two limits to be valid to be a case 12 hole. Then we can, during the previous slides, we can easily calculate the formula by replacing B1 and B, and we arrive at this equation. On the x-axis now, we put the dimension, the smallest dimension of the reservation, alpha 1, within its limits. And we put on the y-axis the bearing capacity and a function of alpha 1 for a fixed alpha. This is for a square slab, this is for a rectangular slab. And you see that within those limits of alpha between 1 and 2, that the minimum changes from this to this point and to this point. All loads are below 100%. So it means reservation of type 12 leads always to a loss in bearing capacity. Let's look at square slab. The red curve, we see that the maximum occurs at alpha 1 equals 0.39, then it's 10% loss in bearing capacity, which is this kind of situation that you will have. We look now at alpha equals 1.5. We see that the maximum occurs here, and you have 90.3 bearing capacity, which is this situation. And finally, the green curve, we have 91% bearing capacity. So these are the three cases corresponding with the maximum losses of bearing capacity. So to sum up, a hole type 12, following the yield line of a rectangular concrete slab leads to a loss of bearing capacity of maximum 10%.